Imagine you're a tiny electron, smaller than a speck of dust racing toward a solid energy wall. In our everyday world, you'd expect to crash and stop, much like a soccer ball hitting a brick wall. But in the quantum world, something truly extraordinary happens. You might disappear from one side and reappear on the other as if you've passed through a ghostly doorway. This phenomenon is called quantum tunneling, and it's one of the most fascinating effects in all of physics. For decades, scientists could only infer tunneling from indirect evidence, since it happens in less than a billionth of a second. But thanks to the Nobel Prize-winning breakthroughs of 2023 and 2025, we now have the tools to observe and even harness this invisible process. Let's explore how these discoveries have opened up the quantum world. Electrons aren't just tiny balls, they're more like blurry waves of probability. Picture ripples spreading across a pond. Even when they hit an obstacle, part of the wave leaks through. That's the heart of quantum tunneling. The thicker the wall, the lower the chance, but it's never truly zero. This behavior is rooted in the Heisenberg uncertainty principle, which says you can't know exactly where a particle is and how fast it's moving at the same time. This built-in fuzziness allows electrons to briefly borrow energy and tunnel through barriers, all within the rules of quantum mechanics. Superposition adds another twist. An electron can be in two places at once, both reflected and tunneled, until it's measured. These principles aren't just theoretical, they're the foundation of quantum computers, where qubits can explore millions of outcomes simultaneously. Quantum tunneling isn't just a laboratory curiosity, it's at work all around us. Your phone's memory, for example, relies on electrons tunneling through a thin insulator to store data. The sun itself is powered by tunneling, allowing protons to fuse despite their natural repulsion, creating sunlight that's sustained life for billions of years. Medicine, scanning tunneling microscopes use tunneling currents to map surfaces atom by atom, and new Etoscan technologies are helping scientists probe biomolecules faster than ever, promising advances in early disease detection. But tunneling isn't always helpful. In microchips, it can cause unwanted leaks and errors. Yet it also powers LEDs, lasers, and even the process behind carbon dating. The double-edged nature of tunneling makes it both a challenge and a powerful tool for innovation. Nobel Prizes of 2023 and 2025 marked a turning point in our understanding of quantum tunneling. In 2023, Pierre Agostini, Ferenc Krauss, and Anne Huilier developed Etoscan pulses of light, so brief they can freeze electron motion, allowing us to observe tunneling as it happens. Their work didn't film tunneling like a movie, but it made it possible to measure electron behavior during the process with unprecedented precision. And in 2025, John Clark, Mitchell H. Devoret, and John M. Martinis were honored for engineering macroscopic tunneling in circuits. They built Josephson junctions, tiny barriers where entire circuits can tunnel between quantum states. These breakthroughs span the quantum scale, from atomic-level dynamics to large functional quantum devices, laying the groundwork for practical quantum computers. The impact of these Nobel-winning breakthroughs is already reaching into our daily lives and shaping the future. Ultrafast tunneling spectroscopy is helping researchers simulate protein folding and charge transfer, accelerating drug discovery. Quantum tunneling models are guiding fusion energy experiments, bringing us closer to clean, limitless power. Macroscopic tunneling enables quantum sensors that can detect magnetic fields with extreme sensitivity, and GPS-free navigation is becoming a reality. Most notably, stable qubits built on Josephson junction tunneling are scaling up quantum computers, moving them from theory to practical machines. We're no longer just observing quantum magic, we're building with it, engineering the invisible to solve real-world problems and unlock new possibilities.